Hello everyone, and thank you for watching this talk that's part of the SIME UQ Mini-Symposium on Probabilistic Numerical Methods for Cubature. I'm Alex Gessner from the University of Tübingen, and I'll be talking about integrating and sampling from Gaussians under linear domain constraints. This is joint work with Andri Lakhanjilal, who is now at the Technical University of Munich, and Philipp Hennig. Now this talk should bear a huge warning sign saying, "This is not a probabilistic numerical method." Nevertheless, I thought I'd talk about this project because we all know that Gaussians are a common choice in probabilistic modeling, more specifically probabilistic numerics, for their nice properties. And there are countless examples in which likelihoods naturally impose restrictions on the domain space. We'll see a few of these examples later. With this talk, I hope to provide a useful tool that allows to integrate linearly constrained Gaussians and to draw samples from the domain of interest at the same time. Okay, let us define the domain of interest as where m linear functions in a d-dimensional space exceed 0. Now the goal is to estimate the probability mass that a point x falls into this domain under a standard Gaussian measure. Now the challenges are that this probability might be extremely tiny. Just think about an orthant in a d-dimensional space, the mass of which in a Gaussian is 2 to the minus d. And then, of course, the high dimensions are an additional challenge. And, another goal is to also sample from this domain. Normally, we think that the number of constraints is larger or equal than the number of dimensions, because otherwise you can rotate the problem such that you can integrate out dimensions to get the same number of constraints and dimensions. Let's first look at the sampling part. Our proposed sampling algorithm is an adaptation of elliptical slice sampling that becomes particularly elegant in the linearly constrained domain. First of all, a quick reminder of what elliptical slice sampling was and how it works. It's a Markov chain Monte Carlo algorithm that allows you to draw samples from a posterior where the prior is a multivariate normal. Given an initial location, it does so by drawing an auxiliary variable from the multivariate normal and constructing a one-dimensional ellipse, and then sampling from this ellipse in a slice sampling manner. So that means you draw a likelihood threshold between 0 and the value of the likelihood at your current location, and then only admit points that exceed this likelihood threshold, and you do this by a stepping out procedure. Now, the beautiful part in our algorithm is that we're dealing with a 0-1 likelihood, so you don't need to care about a likelihood threshold because either a sample falls inside or outside the domain. And then also in standard elliptical slice sampling, you need to find the slice where the likelihood is larger than your likelihood threshold. And you do this by drawing proposals and rejecting them if the likelihood value is smaller. Now in our case, this is a lot easier because intersections of the ellipse and these linear domain boundaries have closed form solutions. That means given a sample that is already in the domain, we can immediately build up the bracket that we can sample from, and we just need to draw one random uniform number to find the next sample that lies within the domain. That means, in this case, the algorithm actually samples entirely rejection-free. Now with the sampling algorithm at hand, we will use the Holmes-Diaconis-Ross algorithm for integration. This algorithm is a multi-level splitting technique. It originates from the rare event estimation community. The goal there is typically to estimate the failure of, say, a mechanical system, which is commonly a very small probability and correspondingly hard to compute. The key idea of these multi-level splitting techniques is to decompose the integral into a product of conditional probabilities that are easier to estimate. These conditional probabilities can be constructed through a set of nested domains. Let's look at an illustration of how this algorithm works. So let's say we're interested in the mass of this blue domain here that is restricted by these three linear functions, and that we're already provided with a nested set of domains that are given by these other lines that you can see here. Now the first step is to sample from the entire domain, which for us means to sample from the Gaussian prior. Then the algorithm checks how many, or the fraction of the samples that fall into the first, like the largest next domain, and saves this fraction. And that's the conditional probability of falling into this domain given samples from the entire domain. And now with our algorithm, with our sampling algorithm, we are able to sample directly from this linearly constrained domain and then proceed the same way again, like sample from this domain and check how many samples fall into the subsequent domain and save this fraction. And we can proceed this way until we reach the final domain that we're interested in. And this way we can compute this the normalization constant with these conditional probabilities. The shifts here we've defined through scalar shift values. So by just adding a scalar for each domain to the linear functions, we obtain like a nested set, and so these values are larger than 0, and we'll see later how we get them. The Holmes-Diaconis-Ross algorithm requires this sequence of nestings defined through the positive shifts in order to simulate from the respective domains and then check how many samples, or what fraction of samples falls into the next domain. Crucially, it's also able to compute the logarithm of the normalization constant, because you can obviously always compute the logarithm of these conditional probabilities and consider the sum of those. The success of this algorithm really depends on that shift sequence. So you can see, for example, if no sample would fall into the subsequent domain, then the entire thing breaks and the estimate for the normalization constant is just 0. In the rare event estimation community, these shift values are often chosen in an ad hoc way, but there you essentially run into the danger of having very imbalanced conditional probabilities. Ideally, you would want to have the probability for a sample to fall into the next domain to be 1/2. Conditional probability of 1/2 maximizes the entropy of the binary distribution of whether a sample falls in or outside of the nested domain. So we're looking for some procedure that gives us a reasonable sequence of nested domains that the Holmes-Diaconis-Ross algorithm can work with. To choose the nested domains, we use an algorithm that is very similar to HDR and is called subset simulation. The difference is that here we fix the conditional probabilities to 1/2 and then sample and choose the nestings such that the desired fraction of samples falls into the next domain. Again, here we can use the elliptical slice sampler that I presented before that allows to sample rejection-free from these domains until you reach the desired domain and you're left with a sequence of nestings that have approximately probability of 1/2 for samples to fall into the next domain. Now, subset simulation can evidently also be used to compute the integral or to estimate the integral, but this integral estimator is biased as opposed to HDR, and that is why we use subset simulation to construct the nestings and HDR to compute the integral. To get a sense for how subset simulation works, we're looking at a 500 dimensional toy problem that has an analytic solution where the integral has a value of roughly 10 to the minus 38. We draw a different number of samples per nesting to construct the nested domains and to estimate the integral at the same time. So you can even go ahead and start with 2 samples only, and just draw 2 samples from each domain to construct the next one from 1 sample only, which is obviously bad, specifically because we're dealing with a Markov chain Monte Carlo algorithm. So samples are dependent, and in this case, even I think I skipped a couple of samples every time for the elliptical slice sampling procedure, but nevertheless the integral is terribly underestimated. I should first make clear what we actually see in this plot. So the x-axis shows the number of subsets as well as the negative binary logarithm of the integral estimator, and this is equivalent because we've been choosing the conditional probabilities to be exactly 1/2. And now if subset simulation finds t nestings, the estimator is roughly 2 to the minus t. So there should not be a logarithm that's wrong here. But so essentially on the y-axis here you see these shift values for a different number of samples per nesting chosen. And here, looking at 2 samples only, we can see that that the nestings extend to more than 300, and so the corresponding integral estimator would be 2 to the minus 300, which is way too small, given the true value, which is indicated as the vertical line. And on the right-hand side, you can see a different axis, which indicates the number of samples that are also color-coded here, drawn per nesting, and here are the integral values tracked. So you can see that the integral values indicate where these nesting sequences end for subset simulation. And now we've been running this for different numbers of samples, and well, obviously the more samples you draw, the better you get. But we saw that that here 2, 4, 8, 16 samples already gets reasonably close to the true integral value. And since we're not trying to estimate the integral with subset simulation, but HDR instead, and we're only interested in the sequence, we decided to stick with 16 samples per nesting for the subset simulation, and this runs really fast, so this can be seen as some sort of pre-processing step for the Holmes-Diaconis-Ross algorithm to compute an unbiased estimator of the integral. For the same problem, we can also look how the choice of number of samples for subset simulation affects the integral estimate by HDR. So on the right hand side, you can see the number of samples drawn by subset simulation to estimate the shifts row, which according to subset simulation are 1/2, right? But if we draw very little samples, we can be arbitrarily bad. And on the bottom, you can see this conditional probability as estimated by HDR. So you can see that if we draw only 2 samples in subset simulation, then many of the conditional probabilities found by HDR are a lot larger than 1/2, while the more samples we use with subset simulation to estimate the shifts, the closer the conditional probability that HDR finds centers around 1/2. Now on the left, you can see the integral estimate as done by HDR for the same number, also here for the number of subsets, the same color coding as before. So these the dark blue line is the integral estimated when only 2 samples have been used for the subset simulation. And you can see that here, like on the x-axis, you can see the number of samples per nesting used for an HDR. So if we give a bad nesting to HDR, then the integral estimate is also going to be bad. And the better the nesting is, the better also the integral estimate through HDR. And here only the top plot shows the binary logarithm of the integral estimator, and below is the relative error. And there it's just important to keep in mind that if you are just an order of magnitude off, which in this case is like, say, 10 to the minus 39 instead of 10 to the minus 38, then the relative error is already pretty close to 1. So whenever you see a deviation of 1, we're already in a good order of magnitude for the integral estimate. So the bottom line here is HDR does require a good nesting to come up with a good integral estimate, and therefore we fix the number of samples used per subset to like a good trade-off between fast pre-processing and a good nesting. Let's look at a few examples where such integrals arise. One of them is entropy search, which is a Bayesian optimization algorithm where the search strategy is to evaluate the location that is most informative about the minimum. Now, for that, you need this quantity, the probability of the location xi to be the minimizer of the function f that you want to optimize. And this by itself is an intractable quantity because essentially you would need to compare f of xi to infinitely many other locations xj. But in the algorithm it's approximated through a set of representative points, which are here indexed by j. And then to compute the probability that f is smaller at xi than the others, you need linear constraints to cut off the cases in which any of the xj has smaller function values. So this is an integral that we can solve with the presented algorithm. In the original paper, the authors use expectation propagation to compute that integral, and we can see here on the top plot an example for a Bayesian optimization problem where the greenish line shows the ground truth obtained by sampling for this integral value, and the gray line shows expectation propagation. And so you can see that in some cases it's quite okay, but then in others it gets arbitrarily bad. And specifically, if this probability gets really small, then expectation propagation just drops down to 0, which is not quite visible here. We've used our algorithm only at the 4 locations indicated here and ran it, and so we can see that over time at least it can get better. So EP is really fast and sometimes also provides quite reasonable estimates, but specifically in cases like here the orange one, where the probability is really small, entropy expectation propagation just fails, while our algorithm improves over time. Now, at the moment, this algorithm is still fairly slow, but then HDR is highly parallelizable, which in practice has not been done yet. And because for every nesting you can sample in parallel essentially and compute these fractions and add them up later. Bayesian optimization holds also an example for where sampling from a linearly constrained multivariate normal is required, or at least interesting. In predictive entropy search, one wants to condition on the location of the minimum, and the distribution over the function conditioned on the location of the minimum is intractable. Well, because it is a linearly constrained Gaussian. But at least we can draw samples from this distribution as shown here on the right. So we're conditioning on this location to be the minimum, and you can see it's pretty unlikely to observe the minimum of the function right here. In fact, this probability is 10 to the minus 6. So if we wanted to sample directly from the Gaussian process, or from this discretized Gaussian process to find these samples, we would need to reject a crazy lot of samples. And in our case, we can just use subset simulation to find one sample in the domain, which goes really fast, and then with the elliptical size sampler, just sample rejection free from that domain. And here, the thin lines show just a couple of these samples, and then their expected value. So we could approximate this distribution by summary statistics, for example. Also, the rejection-free way of sampling allows us to compute derivatives with respect to parameters of the Gaussian, because they can be written as expectations, and with our efficient way to sample, we can compute these expectations via sampling. A final application I would like to highlight is probabilistic tree search that Julia Grosse has been working on for her master project. She's also provided me with these slides. Thanks a lot for that. So the idea here is that we've got a two-player game, and we've got a max player who is trying to maximize reward, and a min player who's trying to counteract. And in the beginning, before you know anything, you put a Gaussian prior over this gain variable at the parent, and then model the children also as Gaussians conditioned on the parent variables. Now, as observations, you can play the game at random, and then observe the leaf nodes, which contain information of whether you observe a win or a loss. And now, if you observe a win, then you know that these gain variables, that the gain variable at the leaf t has to be larger than 0, and if it's loss, it's the other way around. So this brings in a linear constraint, and you want to propagate this linear constraint back to the parent node to gain information about which move to play as the max player, and then the same for the min player. At the leaves, this looks like that. You get, so say we observe a win at leaf T1, which is here on the x-axis, that constrains the g values to be, or the score values to be larger than 0, and we observe a loss at the leaf T2, which constrains the scores there to be smaller than 0. Then essentially we've only cut out this part of the Gaussian, and now the elliptical slice sampling algorithm allows to simulate rejection free from this domain, and then also from the kind of back propagated Gaussians. So essentially you can propagate all these samples up to the highest parent node. And Julia used this as a ground truth in her model. With this, I get to the end of my talk. Let me quickly summarize. We've been looking at multivariate normal distributions under linear domain constraints, and I've showed you an algorithm that allows you to draw rejection-free samples from such a domain, no matter how small the probability mass in there is, and it only requires an initial sample from that domain. But I've also showed you how to get that. You can use subset simulation to very efficiently drive you towards that domain and provide that first sample, and at the same time a nesting that's required by the integration scheme that I showed you and that works for arbitrarily small probability masses, specifically because it can compute the logarithm of the integral. This work has been done together with Henri Lacangélal and Philipp Hennig, as mentioned in the beginning, and you can find the paper in arXiv, as well as the code on GitHub. Thank you very much for listening.